Welcome back to Tokenization from scratch. So far, every token we've made came from data. Today we add a different kind of token entirely, control tokens that we assign by hand that mark the boundaries of a conversation. These are how a base model becomes a chatbot. We'll register them, protect them through encoding, and use them to turn a real chat into a single stream of token IDs. Quick recap of episode 4. We stopped tokenizing characters and started tokenizing raw bytes. That gave us a fixed base vocabulary of 256 byte values, with our learned merges layered on top. Because every possible byte already has an ID, nothing is ever out of vocabulary. Today we build on exactly that vocabulary. Here's what bytes alone can't express. When you chat with a model, something has to mark where your message ends and the model's reply should start. That's what special tokens do. End of document separates training documents. Start of turn and end of turn wrap each message. Padding fills batches. These tokens mean something by their position in the stream, not by any letters, so we don't learn them, we assign them deliberately. The crucial design choice is where these tokens live. They share one ID space with everything else, but we stack them at the very top, above the byte values and above every learned merge. Bytes occupy 0 through to 55, our merges take the next block, and the special tokens sit above all of it. That way adding a special token never disturbs an ID the model already learned. Here's the registration. We start from 1 past the highest existing ID, so specials always come after the bytes and the learned merges. Each one gets the next free integer and two-way lookup entries. Notice we store the token's text in the vocab too, only so decode can render it. The model never derives these IDs from data. They're hand-assigned, permanent, and unique. This is the heart of the episode. If we just ran BP over the whole string, the merge loop might fuse part of a special token into a neighbor, corrupting it. So we split the specials out first using a regex with capturing groups, which keeps the delimiters in the result. Each special drops in as its own ID, verbatim. Only the ordinary text between specials ever reaches the merge loop. The control tokens are untouchable. The gap encoder is exactly the byte-level encode from episode 3. Take the bytes, repeatedly apply the merge that was learned earliest, and stop when no learned pair remains. Nothing new here, and that's the point. By isolating the specials, we get to reuse our merge logic unchanged, with zero risk of it touching a control token. A chat template is just a convention for laying out turns. This is the ChatML style most models use. Each message is wrapped in a start of turn marker with its role, the content, then an end of turn marker. After the last user turn, we add a dangling start of turn for the assistant. That trailing marker is the cue that tells the model it's now its job to speak. Different model families use different exact strings, but the idea is always this. Now we wire it together. Create the tokenizer, load the merges we trained in earlier episodes, and register our 4 special tokens. We format the chat into a single string, encode it, and out comes one flat list of integers, the exact input a language model receives. Let's run it and look at the real numbers. First, the registry. Our base bytes filled 0 through to 55, and the 2 demo merges we loaded took to 56 and to 57. So the specials begin at 258 and climbed from there. They sit cleanly above everything the tokenizer learned exactly as designed. And here it is, a two-turn conversation as 49 integers. Read the structure. 259 opens every turn, 260 closes it, and the ordinary text in between is byte and merge IDs. Notice the 256 near the end, that's our learned merge firing inside the word hello. The specials and the data live side by side in one clean stream. Visually, this is what protection buys us. The start and end markers become single purple IDs, and the merge loop only ever runs on the blue content between them. It can never reach across a special boundary to fuse, say, the angle bracket of a marker into the next word. The control tokens stay perfectly whole every time. 2 final checks. Each special token appears as exactly one ID, 3 start markers, 2 end markers, never split into pieces. And decoding the whole stream reproduces the original formatted chat byte for byte, lossless. Specials are reversible just like everything else, because decode simply maps each ID back through the vocab. Let's recap. Special tokens carry meaning by position, so we hand-assign them above the learned vocab. Our encode splits them out first, protecting them from the merge loop, and a chat template turns a conversation into one reversible token stream. Next episode we open the vocabulary itself, how a token ID indexes an embedding row, the real cost of vocabulary size, and at last the famous puzzle, why a model can't count the Rs in strawberry. See you there.